Hey guys, so as we've been working on solving projectile motion problems, I have for us today a lab to do. It's really more of a challenge than a lab. If you're working remotely, you're just going to watch me do it. But if you are working in the classroom, you are hereby challenged to do this. Okay. What we're going to do is we're going to take a marble and we're going to roll it off the table. And you need to predict where on the floor the marble is going to land and place a bottle cap there. And your challenge is to hit that bottle cap the first time. You get one try. One try. You are hereby challenged. Let's get to it. Okay, you can see here I've got a ramp, and here's my marble. And I'm going to use a ramp to start the ball moving because it's going to allow me to get a consistent speed. Every time the marble comes off of the ramp, it should be going the same speed. So I'm going to put my marble on the ramp, and then what I'm going to do is I'm going to lay a meter stick out right there, and I'm going to time how long it takes the ball to roll that 1 meter. That's going to allow me to calculate its velocity as it comes off the table. And then, if you follow me over here, you can see I have on the side of the table a meter stick that shows me how tall the table is, and this is going to tell me the delta y, how far the ball is going to travel vertically. And then you'll also notice I have a meter stick along the floor right there. So I'm going to take my delta y, I'm going to take my vx, and I know the acceleration from gravity. I'm going to take those things and I'm going to calculate what the delta x should be, and then I'm going to put bottle cap there, and we'll roll the ball off and we'll see, do we hit the bottle cap? Okay, I've come over here to figure out the velocity, the Vx of my ball. I have a little bit more space on the counter, and we're not actually rolling it off the table this time. So I'm really just rolling it down the ramp and seeing how long it takes to travel this 1 meter, and that'll tell me what its initial velocity is. So here I'm going to roll it, I'm going to time, and we're going to see, we're going to calculate its Vx. Okay, so my marble rolled 1 meter in 2.03 seconds. So its velocity should be pretty close to half a meter per second. Okay, let's go calculate that. Okay, hopefully we all remember that the velocity of an object is equal to its displacement divided by the time. Okay, in the marble I just rolled, its displacement, it rolled 1 meter. It rolled the length of that meter stick, which was 1 meter. And I'm going to count that to 3 significant figures. Let's say it's 1.00 meters. I think I can say that I was that accurate. Okay, now the time is what I measured on the stopwatch there, delta t, and that was 2.03 seconds. Okay, so I know my displacement is 1 meter and my time is 2.03 seconds. Let's put those into the equation and let's find the velocity. So the velocity will be 1.00 meters divided by 2.03 seconds. And I need 3 significant figures in my answer. So I'm going to round to 0.493 meters per second. 0.493 meters per second. Okay, now that number is going to be our Vx. That's going to be the velocity of the ball as it goes off the table. We're also going to want to know the delta y. The delta y is how far it's going to fall. So let's take a look at our meter stick here on the side of the table. How tall is the table? How far are we going to fall? Let's see, let's not read the inches side, let's read the centimeter side. And that looks like it's a little bit less than 92. It's 91 point, it's about 91.6 centimeters. And of course, we're going to want that in meters. Okay, so that is our delta y. Our delta y, we'll say, is 0.916 meters. And like we just figured out, our Vx is 0.493 meters per second. And then the other thing that I know is I know the acceleration in the y direction. That's g, right? So a sub y is negative 9.81 meters per second squared. And let's be technical here. Let's not forget my ball is falling, so that delta y should be a negative. So rather than just 0.916 meters, I'm going to put negative 0.916. So these are my numbers that I'm starting with. Let's go ahead and let's calculate what delta x is. How far along the ground is that ball going to fall? All right, let's calculate how far from the table that ball is going to land. Let's calculate the delta x there. So, like we've just figured out, I know my delta y, I know my vx, and I know my acceleration in the y direction. So just like the strategy that we've been taking on the problems that we've been doing, we're going to do the same strategy here. What I'm going to do is I'm going to use this equation to find the time, to find delta t, and I'm going to take that and I'm going to put it into this equation to figure out what delta x is. So in the first equation here, delta y, I know, is negative 0.916 meters, and then it's 1/2 times ay. I know ay is negative 9.81 times delta t squared. Okay, now I'm going to I can simplify here, 1/2 times negative 9.81. I'm going to bring down my negative 0.916. 1/2 times negative 9.81 is negative 4.90 times delta t squared. I'm going to divide both sides by that negative 4.90. So I'm going to take this number and I'm going to divide by that number. And with three significant figures, I get 0.187. 0.187, and that is delta t squared. And then, of course, we'll have to take the square root because that's delta t squared. So we take the square root of 0.187. And with three significant figures, that means delta t is equal to 0.432 seconds. Okay, now we're going to take that number, we'll put it into this equation, and then we'll figure out what delta x is. So in that equation, delta x is equal to Vx, which we figured out before. We figured out over there. Vx we said was 0.493 meters per second. 0.493. And delta t, which we just found out, was 0.432 seconds. 0.432, kind of similar numbers there, it looks like. So now I'm going to take these two numbers, I'm going to multiply them, and that'll give me delta x. So that means delta x is equal to 493 times 0.432. With three significant figures, that is 0.213 meters. And that's how far I need to put the bottle cap from the end of the table. Be a little bit easier for me in centimeters, so 0.213 meters is 21.3 centimeters. So now let's go and put the bottle cap 21.3 centimeters from the end of the table. Then we'll roll the ball and see if we can hit it. How's it going? So 21.3 centimeters is right there. That's where I'm going to put my bottle cap. And you can see I have a little room, a little leeway there. But let's see if we can't hit it dead center. Alright, so now I've got another computer down there. It's set up to record a close-up of the marble hitting that bottle cap there. Got my marble here. Let's go on up here. Let's roll the marble and let's see if we can't hit that bottle cap. That's how it's done. Alright, so if I'm honest, what you saw was not the first roll of the marble. The first roll of the marble, I hit the meter stick immediately next to the marble. Second roll of the ball, I forgot to hit record on the second computer. Third roll of the ball, what happened third roll of the ball? I tripped over my microphone wire and ruined that footage. Fourth roll of the ball, I noticed that when I bent over to turn on the second computer to start it recording, there's a nice little plumber smile, so I decided not to use that footage. The next roll, anyway, what you saw was probably the fifth or sixth roll of the ball. But I'm going to tell you what, I hit the meter stick next to the bottle cap the first time, and then I hit the bottle cap 5 or 6 times after that. So anyway, if I'm honest, what you saw was not the first roll of the ball. But you didn't see the first, hit because of technical issues. Anyway, I go on. Hopefully, that helps us to be able to solve projectile motion problems. So until next time, take it easy.